Hello everyone, I'm Pierre Mézières, PhD student in France at the Institut de Recherche en Informatique de Toulouse. My talk will concern the recursive analytic spherical harmonics gradient for spherical lights. In this work, we use the spherical harmonics basis functions that are widely used in computer graphics. Spherical harmonics are orthogonal basis functions that allow to efficiently represent any function defined on the sphere by an angular frequency decomposition. They are defined by an order L related to the function frequencies and a degree m related to their orientation. In practice, spherical harmonics are band limited to a given order L, which fixes the highest representable frequency. The case m equals 0 is a subbasis called the zonal harmonics that are useful to represent circularly symmetric signals. However, computing the spherical harmonics coefficient representing the radiance at each shading point is costly, and it quickly becomes intractable to project the radiance onto the spherical harmonics at each frame for close-range lighting. To reduce this cost, Wu and colleagues proposed to compute the spherical harmonics coefficient only on a sparse grid to interpolate them at each shaded points. They also compute efficiently the gradient of the spherical harmonics coefficient representing the radiance field produced by polygonal lights to construct an accurate Hermite interpolation. Our contribution used the exact same pipeline, but efficiently computes the gradient of the spherical harmonics coefficient of the radiance field produced by spherical lights. Mézières and colleagues propose an efficient spherical harmonics projection for spherical lights. While looking at the radiance field of a spherical light arriving at a point x, the function is circularly symmetric, so only representable by zonal harmonics. They derive an efficient recursive equation to compute the zonal harmonics coefficient. Then, they retrieve the spherical harmonics coefficient by applying the zonal harmonics rotation proposed by Sloan and colleagues. To compute the spatial gradient of the spherical harmonics coefficient, we need to compute the gradient of the zonal harmonics rotation with respect to the position of the point x. By doing so, we obtain this equation, where the blue parts are already computed efficiently by Mézières and colleagues, and Sloan that proposes an efficient method to compute the spherical harmonics basis function. The red parts are respectively the gradient of the blue parts that we propose to compute efficiently. It is important to note that we are looking for the gradient with respect to the shaded point x, but it is simpler to write the gradient of the spherical harmonics and the gradient of the zonal harmonics coefficient with respect to the position of the light y. Thus, the gradient that is computed is the opposite of the one we are looking for, since moving the point x along an axis is equivalent to moving the point y along the opposite axis. In the first time, the computation of the gradient of the zonal harmonics coefficient is the direct differentiation of the equation proposed by Mézières and colleagues. This is straightforward and given in the paper. What's more interesting is the efficient computation of the gradient of the spherical harmonics basis function. Spherical harmonics are naturally defined with spherical coordinates where k is a normalization factor and p are the associated Legendre polynomials. The partial derivative of the spherical harmonics with respect to phi is a scaling of the spherical harmonics basis function, therefore easy to compute when the spherical harmonics are already evaluated. The partial derivative with respect to theta is a bit more complex but straightforward to compute when the derivative of the associated Legendre polynomials are known. However, as we will see in the resulting timing, this method is efficient, but there is a more efficient method. Sloan, in 2013, proposed an efficient method to compute the spherical harmonics basis function. Looking at the spherical harmonics definition, as well as the definition of the associated Legendre polynomials, the green parts and the red parts can be matched together to construct efficient recursive relations. By removing the sin theta m from the associated Legendre polynomials, they become a polynomial in Z that is, as shown by Sloan, efficiently evaluated with 5 recurrency relations. It should be noted that if the spherical harmonics are naturally defined with spherical coordinates, an efficient method to compute them is by using a polynomial form based on the Cartesian coordinates. However, this approach remains slower than the method proposed by Sloan. To apply the same principle as Sloan, we need to find the same sin theta m factor in the derivative of the associated Legendre polynomials. By doing so, we found this equation, where the QLM are the recurrency relation proposed by Sloan, and the TLM are their derivatives. However, it should be noted that at the end, we need the spatial gradient with respect to the Cartesian coordinates, whereas until now, we compute the gradient with respect to the spherical coordinates. It means that the change of variable must be done by multiplying each spherical harmonics gradient by the Jacobian of the transformation from the spherical coordinates to the Cartesian coordinates. Even if this step costs computation time, this approach is very efficient. Indeed, our approach outperformed the polynomial form of the spherical harmonics. Even though using the polynomial form, the gradient is directly computed with respect to the Cartesian coordinate, since the polynomial form is based on the Cartesian coordinates. Here, each column corresponds to a spherical harmonics band limit. The first three rows evaluate the time to compute the spherical harmonics and their gradient using the polynomial form. The fourth row corresponds to our method using the Sloan-like method. If the evaluation of the spherical harmonics and their gradients can easily be evaluated separately using the polynomial form, this is not the case for our method, notably because the partial derivatives with respect to phi directly use the evaluation of the spherical harmonics basis function. But also, the recurrency relations to compute the spherical harmonics function and their gradients are combined together. However, even when separating the computation, using the polynomial form to compute only the gradient is only more efficient for less than 4 spherical harmonics bands. Furthermore, computing only the gradient seems to be an awkward use. Also, using a direct definition of the derivative of the associated Legendre polynomial, shown in this last line, is less efficient than our proposal, while remaining more efficient than the polynomial form. Now, we know how to compute every term efficiently. But before discussing the results, let me introduce our polygonal light approximation model. We focus our approximation on triangular lights, as any polygon can be divided into triangles. We position the spherical light at the barycenter of the triangle, and the radius of the sphere is determined so that the triangle and the coplanar disk have the exact same area. And the spherical harmonics coefficients are scaled by the term cos gamma to take into account the normal of the triangle and thus correct the energy due to the flatness of the triangle. This means that the gradient of the coefficient needs to be adapted, but this is straightforward and given in the paper. Last but not least, before mentioning the results, it is the loop organization that is crucial for the performance of our method. While the natural approach, which we called here the forward approach, consists in looping over all the light to accumulate the spherical harmonics coefficient and their gradients, this approach requires to store in memory all the coefficients and the gradients for all the spherical harmonics, which increases the pressure on the registers in the parallel implementation on GPU. To avoid this, we propose to swap the first two loops that we call the reverse approach. This means that this approach stores in memory only the coefficient and gradients corresponding to 1 degree m, hence strongly reducing the pressure on the registers. As can be seen in the table, this loop organization greatly improves the resulting timings. The first two columns, the analytical columns, correspond to the case where the spherical harmonics are computed using the polynomial form, and the two following ones use our recursive form. Finally, the last two columns shows that our polygonal source approximation is more scalable in terms of spherical harmonics band limit than the reference method proposed by Wu and colleagues. It must be mentioned that the reverse organization of the loops is only adapted to the method of computation of the spherical lights. Indeed, the recurrency relation that we use fixes a degree m and loop over the different orders L, so those two loops can be separated directly. While the computation method of the polygonal lights relies on the general method of factorization on the zonal harmonics, which cannot take advantage of such a simple optimization. We can push our comparison further by varying the number of lights or the density of the grid. And in both cases, our method outperformed the reference method for polygonal lights. In the two graphs, the red and blue curves correspond respectively to our method and to the approximation of polygonal sources. The yellow curve is the reference method for polygonal lights, and finally the black curves correspond to the interpolation, which is independent of the three methods, but also independent of the number of sources or the density of the grid. This independence from the number of lights makes the method particularly efficient for handling several hundred of spherical lights in real time. The plain line shows the computation time without the use of the interpolation, which means that the spherical harmonics coefficients are computed at each shaded points, and the dotted line represents the timing with the interpolation. So the spherical harmonics coefficient and their gradients are only computed on the sparse grid. In terms of quality, we observe the same result as those demonstrated by Wu and colleagues in their work on polygonal lights. The hermit interpolation outperformed the trilinear interpolation, and with a sufficient grid size, the approximation error becomes very small. The approximation error is visible in the insets, which show the absolute error with the reference. Thus, a black image indicates the closeness of our approximation compared to the reference. As we have shown in the computation time, our method is more efficient than the polygonal method, and now we verify that our approximation allows to obtain a similar lighting to the one obtained with polygonal sources. In the first time, we look at the results without the interpolation. So the spherical harmonics coefficients are computed at each shaded point, and the position and the radius of each spherical light are computed from the triangles with the method exposed some slides before. And the energy of each light is corrected to take into account the normal of the triangles. Using a traditional real-time bands number between 5 and 9 spherical harmonics bands, our results are very close and difficult to distinguish with the naked eye, while having a much more efficient computation time, especially when using 9 spherical harmonics bands. We obtain the same result with the use of the interpolation. In this figure, the left column corresponds to the use of spherical lights, the middle column to triangular lights, and the right column corresponds to our approximation of triangular lights. In the case of the spherical lights and our approximation, the spherical lights are positioned at the exact same location and have the same radius computed according to the triangles. The only difference in our approximation is the correction of the energy for each light to take into account the normal of the triangles. Top line compute the spherical harmonics coefficient at each shaded point, and the bottom line use the interpolation. Even without the energy correction, the spherical lights allow obtaining a very close lighting to the one produced by the triangular lights. However, the inset, always showing the absolute error, proves that the energy correction results in a very small approximation error of the polygonal lights, while keeping computation time much more competitive than with triangular lights, even with the use of the interpolation. However, if our approximation method worked well with not two degenerated triangles, we identified two main failure cases of our polygonal source approximation. The first case is the use of narrow triangles. Each image shows the quality of approximation of our method using different heights for an isosceles triangle. Each image is divided in two, with on the left the lighting obtained with the triangle, and on the right the lighting obtained with our approximation. The insets show the absolute error between the two results. We notice that when the height of the triangle increases, the approximation error also increases because our method only positions a sphere at the barycenter of the triangle. The second case is the use of large triangles, or by analogy, the case where a triangle is moved closer and closer to the shaded surface. In this case, the error increases because the spherical light, due to its spherical nature, get closer to the surface, creating an overestimation of the lighting at the center of the reflection and an underestimation of the lighting close to the reflection of the vertices of the triangle. This is particularly noticeable in the error inset of the last image, the one using the larger triangle. However, a big limitation arises in this kind of method due to the pipeline construction. While we show an efficient method to compute the gradient of the spherical harmonics coefficient that is scalable in terms of spherical harmonics bands, the interpolation is problematic due to the big number of memory accesses that need to be done at each shaded point. Indeed, each shaded point needs to retrieve the spherical harmonics coefficient of the neighboring probes as well as the gradients that multiply by 4 the number of memory accesses. In addition, the number of coefficients is quadratic to the number of harmonic bands, which make particularly problematic the use of many harmonic bands when the memory bandwidth is not sufficient. Our proposal is really close to two hot topics in computer graphics, that are the neural gradients field and the differentiable rendering. The neural gradients field approaches have the same purposes as our approach, that is the efficient reconstruction of the gradients field. Thus, our approach can be used as a direct application in a nerve-based method. Also, computing the gradient of numerous rendering quantities is at the heart of differentiable rendering approaches. Hence, our proposal to differentiate the gradients field produced by spherical lights can be used as a building block to construct an efficient differentiable rendering method. In conclusion, our method does not surpass the traditional limitation of the spherical harmonics. Indeed, spherical harmonics act as a low-pass filter, which is particularly visible on the glossy reflection on the armadillo when comparing the rendering obtained with the recasting and the rendering obtained with the spherical harmonics. However, the method of interpolation of the spherical harmonics coefficient allows to drastically reduce the computation time while having a result very close to the method without interpolation. As well, our method allows using several hundreds of spherical lights in a real-time framework, which allows, for instance, to simulate complex patterns at low cost, such as textured lights. Thank you for listening, and I hope you enjoyed this presentation.